Our next speaker is Julian Hänig from TU Dresden. Julian studied at Dresden. He graduated with a dissertation on laminated thin glass, and he was telling me that he's just submitted his PhD final thesis, so he's going to defend it a week on Monday, so good luck for that. And today he's going to talk about a product that comes out of the research that he's done, NEERO-Façade, and is a new concept of facade design with lightweight, thin glass plastic composite panels. And the floor is yours. Thank you.
Thank you very much for your kind introduction. Hey, welcome everybody. So still some people here. I try to keep the time so that we can go and get a beer and then later on the dinner. I said already, I would like to introduce you a new facade concept based on lightweight, thin glass plastic composite panels that are based on my PhD thesis. And it is called NEERO-Façade. So, well, double facades, we know they consist of two layers. So the inner facade layer, primary facade, and an outer secondary skin. So the outer glass layer improves the thermal efficiency and also the user comfort for the inhabitants. So the barrier glazing, as we can see in these two examples, have to be very transparent. And due to the high self-weight of glass, sometimes we need really those kind of substructure that we can see that reduces the transparency. So also fixings like here on the right-hand side, and we have a very massive structure. So that's why I was looking into a new product and how to get this high transparency as is required by the architects and allow for an open space. And how can we save also resources here for the substructure and the fixings and the complex design. Thin glass is a new material that's coming more and more into focus. And in this case, with lightweight composite material, I was investigating. So conventional glass, I think we all know, we talk about 2 to 25 millimeters. And when it comes to thin glass, we talk about 2 millimeters or even less. So this reduces the dead weight, first of all. Then we save resources in production. And we have a very low intrinsic stiffness, so high flexibility. However, this is not sufficient for any load-bearing application, especially an architectural application we are looking for. So that's why the idea came up to form sandwich structures with a lightweight plastic interlayer core to stiffen the material. This can be seen here, the glass structure. So we have a thin glass plastic composite panel, they are also called NEERO glass. And it consists of 2 thin glasses. And within, there's a PMMA interlayer core that is directly casted in between the thin glass, directly connected with a chemical bond, and therefore we don't need any additional PVB or additional interlayers to connect the 2 materials. Due to the lower density of the PMMA itself, we have a high weight reduction. When we talk about 12 millimeter glass, compared to the thin glass plastic composite panels, we have a weight reduction of 45%. So very high, and this is the idea to bring into the facade. But let me sum up the thin glass plastic composite panels. So we have an interlayer core of PMMA, which is already applied in facade engineering, so as a replacement, lightweight replacement for the building industry. However, we have a low scratch resistance and also less stiffness, especially when we compare it to glass. Therefore, we use outer thin glass layers to stiffen the panel. Either we can use annealed glass or chemically strengthened glass also to increase the strength of the panel. And due to the full composite bond, we have a full transparency. As conventional glass, high optical qualities, we can also grind and polish the edge. And we have a high durability due to the cover layers of thin glass. When it comes to the structural performance, it's also very high due to the thin glass at the outer layers, and even PMMA provides us sufficient stiffness for those kind of applications in the building industry. When it comes to the strength, it's equal to the glass type. So when we use chemically strengthened glass, we also can achieve higher strength within the composite panels. So we have an increased material efficiency compared to conventional glass. So it's lightweight, and it offers a transparent solution. That's what we are aiming for. And we have a less resource consumption, especially when we compare it not only to the material itself, but also the overall structure. But how to use it now for the facade I was looking for, so secondary skin facade. So this was investigated in a research project with my industrial partners, the manufacturer of these panels. And within the secondary skin facade, here called NEERO-Glass, a new design concept was developed. So we had to combine three main criteria. First of all, the lightweight design with the new thin glass-plastic-composite panels to achieve transparency and an overall slender construction. Therefore, we had to do three customized developments. First of all, the secondary skin, so the lightweight thin glass-plastic-composite panels, NEERO-Glass in short form. An integrated facade fixing, so how can we do a customized fixing for the lightweight panels in order to achieve a higher transparency and slenderness in the construction. Last but not least, the slender substructure, which has to be an appealing and multifunctional design in order to get dematerialization in this facade type to achieve the maximum transparency in the overall construction. Therefore, different construction variants were investigated. So first of all, the 1 to 3 is showing an integrated fixing at the lower part that is directly integrated into the PMMA interlayer core. And the substructure itself is an extended structure, I would say here. For 4, we can see an integrated cable that goes through the PMMA, and therefore it's a tensile supported structure in this case. And on the other side, we have a self-supporting structure with self-standing and integrated connection. Different of these were investigated, but we concentrated later on the extended structure with integrated facade fixing, because this allows maximum flexibility in the design due to the integrated fixing and then an extended structure. So as you can see here as a small rendering. How was the development of the integrated facade fixings? Therefore, 4 different processes and steps were done. First of all, the structural design of such a fixing. Therefore, we had several design possibilities we considered and investigated as a customized point connection. For the adhesive connection, we had an adhesive selection study to have a transparent adhesive that is working with the new material. Numerical analysis were performed in ANSYS and RFEM to find the proper dimensions for our facade fixing and to optimize the design. And last but not least, experimental testing at the university. So what are the load-bearing performances, what are the capacities, and to prove the connection. The structural design later on uses 2 main joining methods. So the main loads, variable loads, wind loads, etc., are transferred via the transparent adhesive joint at the back side of the fixing. With an adhesive 2-component polyurethane, it is connected to the glass surface. And we have additionally an integrated connection, mechanical connection, so directly screwed with fasteners into the PMMA interlayer core. And therefore, we also have a mechanical connection that carries, first of all, the dead loads and also provides a mechanical backup in case of adhesive failure. On the right-hand side, you can see the dimensions which were used later on in the facade case study. And of course, the NEERO-Glass itself is designed or dimensioned according to the expected loading. We can see here a final design. So we have a transparent adhesive that is used. It was filled on the back plate here with a small hole, and the 2 fasteners that are directly integrated into the PMMA interlayer core. So we have a transparent adhesive joint and the mechanical connection combined in this facade fixing. It can be customized, of course, in size and according to the substructure. And in total, we have a structural connection that was developed here. It allows for an easy assembly later on site because we can prefabricate these fixings and directly integrate it into the core. We have a slender design. This can be seen later in the case study. And it also allows for residual performance in case of any failure of the adhesive joint, but also in case of panel failure due to the PMMA core. How to implement now these fixing into the secondary skin? So therefore, different design criteria were considered. So first of all, the panel stiffness and the facade fixing that we developed already and was introduced. Then a rotation flexibility to later on withstand thermal expansion and also movements, for instance, facade drifts due to overall loading of the building. And of course, the number of fixing points. This also depends on the facade design and therefore the substructure design. For an economic and multifunctional design, we were based on a modular approach. Therefore, first of all, the facade fixing, I explained already, and then we used structural connectors and the facade substructure on a primary facade made of a stick system. So facade fixing, as I said already, is prefabricated, so we just need the structural connector, either an axial joint or a fixed anchor, that is directed to a facade substructure. In this case, I was considering a spider system or also a bracket system, and then a direct attachment to the primary facade. So we don't expect any high dead loads. Therefore, we can use conventional systems that are commercially available on the market for stick system suppliers. So here, a steel plate attachment or a bracket attachment is possible to put into the primary facade. Within the final case study, I would like to illustrate the new facade concept. So therefore, we are here with an office building, with an atrium facade in a standard height of 20 meters in this case, so no high rise. And we developed we designed the double skin facade. So primary facade is a conventional stick system, and the secondary skin based on our new facade concept with NEERO glass panels, so a lightweight design of the glazing itself with 12 millimeter in thickness, and the unit weight is then less than 17 kilograms per square meter. The integrated facade fixing holds the panel itself and is connected to the spider system shown here, and this is directly attached to the primary facade with just screws into the facade design. Maya rendering will finalize and show you the final result. So we have a clear view on the facade, and we mainly see the primary facade. So the secondary facade is nearly not visible, except in an angled view, as you can see here to the right side. So we see the fixings, but in total, I would like to demonstrate here a lightweight design with a high level of dematerialization. To demonstrate this, 1 square meter facade cutout was fabricated and exhibited at the Glassbau Fair in Dresden, conference in Dresden this year. And here on the left-hand side, you can see the prototype in 1 square meter and a filigree design here with high transparency. Of course, you see some labels, but I think it's clear that you see high transparency, especially on the right-hand side when looking from the total front. The secondary skin or the substructure of the secondary skin is nearly not visible and matches directly to the primary facade. So in total, we have a new concept of facade design with these new panels that allow for the requirements for secondary skin glass facades, so we can achieve a transparent design, lightweight design, and a slender construction due to the low self-weight and the new developments within the project. And therefore, we can increase the thermal efficiency, the user comfort, we have new design possibilities, and we have a material-specific construction we developed for these lightweight glazings. Last but not least, we have a dematerialization and therefore a resource saving through the new facade concept that can be done. Next step is now the approval for such a facade for an individual building and to convert now the NEERO-Façade concept into reality. I would like to thank to my partners here that were part of the research project and of course the funders. And finally, of course, a big thanks to you that you're still here and not at the beer bar here outside. But yeah, I think we can discuss it, and thank you.